Hello everyone. Today is the 50th day of Leetcode 75 challenge. Let's begin with the 50th question. Question 2336, smallest number in infinite set. The level of the problem is medium. I will request you to read the question beforehand as I will deep dive into the PPT and explain it in simpler way. Now let's understand the problem in the easiest way possible. So you are given a spatial infinite set that initially contains all the positive integers. Okay. So we have been already given an infinite set which contains all the positive integers from 1 to infinite. Okay. And I'm considering it as infinite because it is said that it contains all the numbers. Now, your task is to implement a class smallest infinite set that supports two operations, which are basically pop smallest. This basically means this method removes and returns the smallest number currently present in the set. So whatever set we have, in that we have to this pop smallest basically return the smallest element it contains. Fine, and add back a number. Okay, this method adds the number back into the set only if it is not already present. Because suppose if you have a set, okay, as it is given to us, and suppose it contains infinite number, and if we have pop, suppose two, okay, suppose two, let two be the smallest number in that. No, we cannot take two. Let's take one to make it more clear. Let's let we popped one, okay, which was the smallest in the infinite set. Now, when we try to add, suppose two using this method, it won't add it because we already have it in the set, right? It is already written there. So only if it is not already present. Since two is present, we cannot add it. But since if it is a one, we're trying to add back, then it will take it in, right? So note that set is still infinite, right? And numbers that were never popped are still considered present and should not be added back, right? Since it is an infinite set, thing which we popped that can only be re-added or added back into the set, right? Otherwise, the numbers which are not popped will remain in the infinite set. You need to design a data structure that efficiently supports both operations while preserving the behavior of an infinite set that starts with all positive integers. Fine, please keep this in mind. Starts with a positive integer, and it's an infinite set. To return the output of each operation as described, managing state between the calls. Fine. Now, consider the problems are the value which will be get is from 1 to 1000, and at most 1000 calls will be made in total to pop smallest and add back. Okay, the question is pretty straightforward. In a layman language, you are given a set. You have to pop the smallest element currently present in the set, or you have to add a new element into the set which has been already popped out. That's all. And if that element already exists in the set, we cannot push it back into the particular infinite set. Fine. Now let's go to the next slide. Now let's understand the input-output explanation. Let's take this example. Okay. So here, if you could see, first the data structure is initialized. So this part is done. Fine. Then add back is called. Okay. And before doing this, please remember we already have an infinite set which contains till 1000 or infinite whatever the number is, right? So we have this set right now. And when we try to do the add back call here, which contains two, it gives null. It does not returns anything because we already have two in our set, right? We have not popped anything till now. Great. Now when we do the pop smallest, what it will do? It will pop the smallest element in the set, which is one right now, correct? Again, pop smallest. After popping, we have the infinite set from 2 to the infinite, right? So it will pop 2 again, right? Then again, if you do the pop smallest, now it starts from infinite set starts from 3 to the infinite, right? So 3 will get popped now because it is the smallest one. Okay. Now after that, when we do the add back, okay, in add back, what we are adding? We are adding 1, right? And since we know 1 is not present in our infinite set, we could do that, right? It will return null because we're not popping out anything, we're adding it. Okay. So again, we will have 1, and since we have popped 3 already, right? So for 4 to infinite, okay, it goes now like this. So when you do the pop smallest again, what you will get? You will get 1, correct? Then again, pop smallest you will get 4. Again, pop smallest you will get 5. So this is what we have to design a data structure to do for. And it was pretty easy and straightforward. So now let's move the next slide. Before going to the further slide, let's understand what is min max heap or min heap or max heap concept. Fine. So what is a heap? It is a spatial binary tree or a complete tree where the value of each node is either, in min heap case, smaller than or equal to its children, max heap greater than or equal to its children. So basically, it stands like this. This is a tree, and if you're looking for min heap, how it works? Okay, let's see here. Every parent node is less than or equal to its children. Suppose If this is -1, it will be 2 and this will be 3. It will be 5, it will be 6. Okay. It will be 10, it will be 20. So if you could see, so this is the parent node and this is smaller than any other node present here for in the children. Okay. 2 is the parent node and 5 and 6 are its children and these children are greater than the parent, which is 2 here. That is what is written here. Every parent node is less than or equal to its children. Okay. The root contains the minimum element used when you use to fast access the smallest element. So basically, every parent element will be smaller than the children element. And for the max heap, it will be opposite. Every parent element will be greater than its children element. So here you could see this is the parent element, right? For this, all the children is below it, and it is greater than the all the children present under it, right? If we take 10 as the parent element, 6 and 5 and 8 are smaller than 10. 10, right? Because 5 and 8 are smaller than 10. Similarly, if we take 11 as the parent node, 2 and 3 are smaller than it. So what is written here? Every parent in a max heap case node is greater than or equal to its children. So basically, if this is the maximum element, okay, all its children will be minimum to it. This is the maximum element. All the children below it will be minimum to this, fine. And this will be minimum to this particular node, but this will be maximum to the below children's, fine. This is how it goes. Now, why it's efficient, right? According to the time complexity, if you could see, insertion takes log n time, deletion of minimum maximum takes log n time, and picking of the element takes O(1) time. Now, here I've done Reheapify. Reheapify is the concept of how the Heapify thing works in a tree, right? How Heapify works. So basically, it means that whenever you delete a node, we have to reorganize the complete tree, right? Or how to delete a node in the middle, or how to delete a node at the end, right? This is what a Heapify does. So this is a different concept or different thing to learn about. I will create a different video for it. Fine. A space complexity comes out to be O of n if we store the elements. Otherwise, zero. Okay, or O of 1. Now, this is mostly efficient for solving the kth largest, smallest element problems, priority queues problems, median finding problems, and heap sort kind of problems. Fine. Where mean max heap is used. Okay. So I've written some kind of questions here, or you could say examples of things where you could use this particular topic. Okay, in priority queues, it is mostly used in C++. You could use this concept. Okay, like elements with high priority are served before the lower priority. Priority queue is basically mean heap only. Okay, and max heap. But in uh, Python, if we focus on Python, there is nothing such as a priority queue directly. Okay, so what we do, we use Heapq to solve our min max heap concept problems. Fine, which is the concept of Heapify also here. Okay, we will learn about this. Now, Dijkstra algorithm uses this min heap concept. Top K problems uses this min heap concepts when we have to find the largest or the smallest element efficiently. Heap sort uses the min max concept and it takes n log n time complexity. Okay. A median of a string use mean heap and max heap together to maintain the lower and upper halves of the data. So these are just the questions, examples, or topics where you could use the mean max heap concept. Okay. So I hope you understood the concept of min max heap. Now let's move to the next slide. To understand what problem is asking, we should build up an intuition to the problem. Okay. Let's do it by understanding the goal first. We are given an infinite set of all positive integers that is clear to us. Okay. After that, our task is to build a class that allows us to always remove the smallest or to return the smallest number in the set. That is done. Okay. There is a class which returns smallest. We have understood that currently, which is whatever the numbers are in the set of that we have to remove the smallest, right? And additionally, we should be able to reinsert previously removed numbers, but only if they are not already in the set. Suppose if the number is already in the set, we are not about to add it, right? Only the numbers which have been popped. Okay. Since the set is infinite, we cannot store all elements explicitly. Instead, we simulate it efficiently. Now, since the question says that the set is infinite, right? So we don't know up to which number it will go, right? Will go to 10 to the power 9 or 10 to the power 10, whatever it could be, right? So we don't know about it, right? So what we could do, we could simulate it from ourselves. I will explain that to you in next slides. To do this, we maintain a counter. Yeah, we counter to the next smallest number which has not been popped yet. and use a min heap for managing the numbers that were popped and then added back. Yeah, this thing looks a bit complicated, but guess about this. Uh, there's min heap and max heap, right? We know about these two concepts. If you don't, please have a look in it. Now, since we have to return the smallest element currently present in the set, this min heap and max heap does it for us, right? Max heap always reinstates the tree or the array and gets back us with the maximum number present in the current set. Similarly with the min heap also. Okay. So what happens is that since we don't know what the infinite number is, in a layman term we can just take a counter, okay, which could start from one, right? And it will keep on going until and unless the complete operation is done. Fine. And we could take min heap concept here and implement for finding out the minimum element present in the current set. Okay. And also after that we could use a set. Why set? Because in a heap to check if a number has already been added back, preventing duplicates in the heap. What happens is that heap does not recognize duplicate elements. If we have two, three times, it will not recognize it, and it will create a chaos for us while we will be iterating the set. So what happens for that? We could use a set because set always takes the unique values in it. This will help us to identify that whether the element is present in the heap or the set or not. Okay, let's understand this more in clear manner in the next slide. Now, let's try to visualize the process. What we could do is we could start with the current, and this is a counter. Okay, we could start with this one because if you remember, the num starts from one. It always starts from one, right? Okay. So first thing comes to our mind is pop. Now pop. Now we know that we are using mean heap. Now, if you are using mean heap, we know that if you use the concept of mean heap, it will automatically give us the smallest element, right? Present currently. Okay. So this will help us to get the smallest element. So if the heap is not empty, of course, if the heap is empty, we cannot do anything about that. But if the heap is empty, if not empty, we remove and return the smallest number from it. Simple as that. Yeah, we will use the mean heap concept and we will just pop the smallest element from the set. That's all. Fine. Now, otherwise, if the mean heap is empty, what we do? If you remember, we have taken the current count, right? Current count is going from 1 to infinite. Suppose we have a 3, 4, 5, and 6, 7, 8. We're standing at 8, right? And we saw that the heap which we had is empty. Now what? It's simple as that, right? We return the current number and move the pointer ahead. Why? If it does not have any, our heap is empty, but our infinite set, which is given to us, or which we are assuming, which is given to us from 1 to infinity, that is not empty, right? That means that we will return this value directly, okay, and move the pointer ahead, or we will make the current to 9, okay, when we are popping the stops. Because heap might be empty. If heap is empty, what are the number which will we get in our current is the smallest number till there, right? That makes sense. Suppose heap is empty and you're standing at the counter 8, okay? That means that this is the smallest element if we add it to the heap. So what we do, instead of adding to the heap, we just return this number directly and we move ahead. Yeah, pretty simple. The pop case was pretty simple to figure out, right? One is use the heap, and if it is not there, we having the current counter to do the stuff. Now, please keeping that in mind, you might forget that we already have a set, right, which contains the infinite number, but we are not making it this out. That is not possible for us, right? But we are keeping this thing in our mind that there is an infinite set and how that infinite set will work. That we are basically reciprocating here. Suppose if you have the infinite set 1, 4, 1, 2, 3, 4, 5, 6, right? And if you have popped 1, 2, 3, 4, 5, and 6, suppose the infinite set continues, right? So you will pop this next smallest element, right? Then you will move. Then this will become 9 will become the next smallest element. This is the same thing which we were doing with the heap and the current. And if the heap was empty, we were returning the current counter value and moving it ahead, right? Okay. Now when we add back the num, or when the add back function is called, what happens? Now this is the important thing. Okay. Let me explain this to you. Suppose this is the infinite set given to us. Fine. 4, 5, 6, 7, 8. Okay, infinite. Now, suppose I am asking you to add, if you remember the example which we discussed earlier in the input output, if I ask you to add 3, according to our question, we cannot add. right? Because we already have 3 in our infinite set, right? So what we will do? We'll do nothing. We'll just move ahead. Okay. Now, since this was a set given to you, and we have popped 1, 2, 3, 4, 5, okay, and 6. We have popped till here. Okay. Now, if I ask you to add 3, is it possible? Yes, it is possible. It will come here and then it will get added in our heap. Okay. Or you could consider this as an infinite set. Now, you cannot, you have to find a logic for this. We have to check this was the last element before 3, right? In our infinite set. So if I call it as a current counter, which means that our current counter value was 7, okay, after popping till here. So if I try to add anything, which any number which is equal to or greater than this current counter, will it be possible? It will be not, because if you try to add 9, you cannot add it because this set contains more values and we have not yet reached 9, or we have not yet popped 9. This with what that means is that we have iterated till 7 till now, or we have popped the values till 7 or till 6 before 7. Okay. So if you ask, okay, pop push 9 into this infinite set, but we already have the value 9 in our infinite set, right? That's why it's not possible to add. But if I say, please add 3, and yeah, the number 3 is less than the current counter. So you will be able to add 3 because this says that you have already popped 3. First thing. Second thing, it is smaller than the current value. Okay. This says that we have not crossed this number or we have not popped anything after this number. Right? You're getting my point in that scenario. So that is what is written here. If the number is smaller than the current pointer, because we are not creating an infinite set, we are using current counter there, right? Meaning it was already popped and it's not already in the heap. We push it into the heap and mark it in the set. Now, why we are using set here, as I already explained, heap does not recognize duplicate values, right? Mean heap or max heap does not recognize duplicate values. So for that, we are using here set so that we can have the understanding whether that value is already present into the heap or not. Or in heap, I mean our infinite set. Okay. Now here the condition is written if the num is greater than current, it is still in the simulated infinite set, so we don't add it back. This also means that the number, as I already explained you, this means that area has not been yet uh, discovered. Just claim it in that way. Okay. So this is the way we can do our create our data structure for this popping and adding the values in our infinite set. So how we can simulate this? Now this is the thing. What you can do? I will just read out the statements because it's pretty easy now. Use an integer current, okay, to simulate the infinite set, because current will, this is the set. Suppose current starts with 1, then it becomes 2, it becomes 3. This runs until the operations are done. Okay, so this creates our infinite set. Suppose if we're standing in 8, this is the current value and we have not explored the values after this. Even though if there is an infinite set given to you, and if you're going serially, of course you will be going serially. Sorry, this will be 9. If you're standing at 9, that means you have not explored the later part, right? Works as the same. Yeah. We use a mean heap to store the numbers that were popped and then added back. We use a set, which will be named as added back, to ensure no duplicates are pushed into the heap. Now, in pop smallest, if the heap is a non-empty value, we pop the top and we remove it from the set also. Because if we remove something from the heap, okay, this is the heap, this is the set, okay. If you remove something from the heap, we should remove it from the set. Why? Because if you have already removed from the heap and not from the set, so we won't be added back into the heap if that particular number comes in the add function, right? So that won't make any sense. So therefore, when we pop something, we pop it from the both. Okay. Else we return the current number and increment it, right? That I have already explained here. And if the num is smaller than the current and it is also not present into the set, then we add it to the heap and the set. Okay. Suppose if the number is smaller, like we try to push 2, we check if it is smaller, yes, and also if we check if it is in the set. Suppose there could be a scenario that we have multiple values of 2, right, in the infinite set. So it might be a case that we have not popped it from the set. That's why we check for the both the conditions simultaneously. Now, what we figured out, We simulate an infinite set efficiently by tracking the current number variable and using heap and set. So we boiled it down of using a counter variable kind of a thing, and then using a heap and using a set, right? This also boils down our time complexity for managing numbers that were removed and later restored, right? This is a pretty good question to have a good grasp of heap and set. Okay, the heap allows us to always return the smallest among the restored number first. Okay, use of a heap, mean heap case. The combination of a pointer is basically a counter, heap, and the set balances the correctness and the performance. So I hope you understood the intuition. Let's move to the next slide. Now, since we got the intuition of the problem, let's look into the approach how we're going to solve it. So step one is initialize the data structures. Okay, but this is basically we want to simulate an infinite set of positive integers, right? Starting from one. So we initialize a variable current. This will work as a infinite set for us, representing the next smallest number in the infinite sequence. We use a main heap. This is the main heap to track the numbers of that we previously removed. We also use the added back, which will be a set. Okay, and why we do this? To simulate the infinite set efficiently and avoid duplicates, adding the numbers back. Heap stores the element. Okay, set for uniqueness. I'm boiling down it to a simple things, and the current is an infinite set. Okay, this are the things how it's helping us. Okay, now in the step two, we try to implement the pop smallest operation. Okay, when pop smallest is called, the first check which we do is if the mean heap has any elements. This is done by this case. If mean heap, this means that if mean heap is not empty, if it is not empty, what we try to do, we take a smallest variable named a variable smallest, and since in Python we use heap q for max and min heap, right? So we will use that here. It's heap q dot heap pop. Okay. Now when we do heap pop, we will pop it from the main heap. Okay. After that, from the set also, what was the name of the set we took it as added back, right? So from the added back, we will remove the smallest element. Okay. Else, suppose these don't work. In else case, what we can do? We can just take the value variable and we can take the current value of the count, right? And we can just return the val. And before returning, we can increment the count also. Okay, that's the thing. So this is what we do in the pop smallest operation to always return the true smallest available number, whether from heap or the current pointer. Now in step three, we implement the added back operation. Now what is the added back operation? Basically adding the elements into the heap, right, or into the set, infinite set, according to the question. So if you remember what we tried to do there, we checked if the number which is given to us to add it back into the infinite set, if it is smaller than the current variable, right? If it is smaller and num is not in the infinite set, not in the infinite set, yeah, correct, but in the set, okay, added back, we named it as added back, right? Then only what we will do, we will push it back into the heap dot heap push the in main heap. I will push this num. Okay, this is how we will do, and same we will add it into the set also. Added back the name of the set, the num. Okay, so and here we won't be incrementing our count because why? Because we are adding a value which is previous to the current, right? So it does not make any sense to increment the count or to move ahead. We have to just stay it back there, right? So this is how and after that, after completing all of this, we don't have to return anything actually because it's class-based functions. So we will just this ensures that only true missing numbers are popped and not yet restored are added back into the simulated set. So this after doing all of this stuff, And when the operation gets ended, we will have the complete answer. So I hope you understood the approach explanation. It was pretty easy and straightforward. Now let's move to the next slide. The code is the exact copy of the approach discussed. Let's understand it line by line. So how it starts is that we take the current, this works as an infinite set, right? I will write it as series. Okay. This is the set, this is the heap. Basically, this is a list which will be used as a heap, right? How it is used, let me show you to you. If the main heap is not empty, this is the heap which we use, right? Heapq is the heap in our Python. Like we in C++ we call it as priority queue, right? That's the same thing. So we do the heap pop because in the pop smallest we're trying to pop the smallest element, and it also we pop it from the set also, and we return the smallest. Simple as that. And if it is not empty, we take the current count value here, increment it, and return it. Simple. And add back function, we check this particular condition. If it is true, we push it back, we push it in the set and into the heap, right? Now the time and space complexity for this code comes out to be, for time it comes out to be log n, and for space comes out to be O of n. Why? Because since we are using min heap, or if you use max heap, anything, the complexity for popping out an element or adding an element is always log n. Okay, because basically the heaps are trees, right? So when you remove this particular element from the tree, the complete restructure is done, and that complete restructure takes O of log n time for adding and popping. Okay, and O of one time complexity is taken for this current variable, which is okay, which is basically negligible. Then comes out to be the space complexity of O of n. Why it is O of n? Because the number of elements which are added back into the heap might be equals to the n size, right? In worst case scenario, in best case scenario, it can be zero also, and in worst case, it can be n also. Therefore, the worst case time complexity and space complexity are log n and n respectively. So I hope you understood the code explanation. Now let's move to the next slide. Now, since we have the understanding of the code, let's look into the diagram of the example. I've taken the same example here. Okay, let's start. Okay, so I've brought down the code also for our understanding. So it starts with the initialization of the data structure. So this will remain empty and it will be none. We can ignore this part. Okay. And after that, currently our current is one. Okay. We have this set. Let me draw this set here. I'm marking it as S, please. Okay. Keep that in mind. This is a mean heap. I will write it as MH. Okay. Anything else? No. We have the smallest. Okay. We'll create a smallest variable here. Anything else? Okay. Current also. We'll increment the current as required. Okay. Great. Let's start. So we have the function called add back. Okay. And since we have an infinite set given to us already, so it contains the values from 1 to infinite. Please keep that in mind. Okay. So what happens? You come to the add back first. Okay. We have the num, which is 2 here. You check 2. Is 2 smaller than the current self dot current? And what is the self dot current value currently? It's 1, right? And 2 is not smaller than current. So it gets falsifies here and we move ahead. Okay. We move ahead. Now, how this is true? Because in the infinite set, we already have 2, 3, 4, 5 up to infinite, correct? Okay, so this still remains empty. Now, pop smallest. What happens? Is self main heap empty? Yes, it is empty, right? So nothing will happen here. Else, well, self dot current. It's one, right? So what happens? In the well variable, here, you will have 1. Okay, then what do? You increment the count. So basically, in infinite set, you are standing here now. Okay, and this has been popped. Then you return the well. When you return the well, it returns 1, right? Because in the well, we had 1 here. So that's what it is. Next. Again, it's pop smallest. You come back here because mean heap is empty now. What you do? You take the current, which is 2 here, right? So this will be replaced to 2. You increment the current from 2 to 3, which is done correctly. And since you have popped this from the infinite set, so this pointer will move here. This is for just imagining for us that how the thing goes, right? That's why I've made up infinite set here. I will add more numbers to it. 5, 6, 7, 8, 9. Okay. And after that, you return the val. Now, when we return the val, what we had in our val, it's 2, right? So we have 2. Great. Again, you go back. We have the pop smallest. Great. Since the heap is empty again, what you do, you put the value in the value part here from the current. You increment the count to 4, and then you return. Simple as that. Now, in, in val, we had 3, right? So we return 3. Great. Now you come back. Now you have add back. In add back, you have 1. Okay. So what you do, you come here, you check 1. Is it smaller than the current sum? What is current sum? It is 4, right? And is it not present in the set? Yes, it is also not present in the set. What you do, you push it into the mean heap and also into the set. Great. And you move ahead. You don't increment the current anymore because it's not required until and unless you pop it. Now you do the pop smallest again. When you do the pop smallest, you come back, you check is the min heap empty? It is not, right? We have the value. So in the smallest variable, you what you do, you call the heap and you pop the minimum element from it. So it's 1, you pop it. Okay. Then you also remove it from the set and you return the smallest. So what is the smallest? It's 1. So you return it. So you could see we have the smallest as 1 here. Okay. Now you go back. This is done. So you go back, right? So when you go back, you check if the min heap is empty. Yeah, it is empty. So you come back to this. Now, what is the current value? It's 4 now, right? And then you increment the current to 5 and you return the val. Now, val was 4, right? So you return 4. Again, you go back, you check is the min is empty. Yeah, it is empty, right? Because you have to pop smallest again. So you come back here, you have the 5, put it here, then you increment the count to 6 and you return the 5 from the val, right? We had 5 in val. So this is what is returned here. And after that, the complete operation is done. And at the end, we get this as the output as we claimed already. So this is how the dry run of our program is completed. So now if you have any doubts or confusion about the solution we arrived at and how we arrived at it, I would suggest going back and understanding the intuition, the approach, the code, and the mean concept if you don't know about that. After that, do a dry run by yourself on 2, 3 examples, and I'm pretty sure we'll understand both the solution and the thought process behind it. So let's move to the next slide. Now, since you're familiar with the problem and the solution, let's move to the lead code and code the solution. So we will start by initializing self.current. This starts from 1 self.added back. This will be the set self.mean heap. This will be a list, Python list. Okay. Now, if self.mean heap is not empty, in the smallest variable heapq.heap pop, we pop the smallest element from self.mean heap. Okay. Then also from the set added back, we remove mm, the smallest element, correct? And we return the smallest element from here. Else, if the heap was empty, then what? We take a value variable and we take the current count, we increment the count, and we return the val. Okay. This says that basically our heap is empty, and currently where we are pointing is the current minimum. Now this is done. Now let's figure out add back. We will check if the num which is given to us if it is smaller than the current and the num not present in the set. Okay. In that case, we push it into the so in min heap we added min heap will add the num and also self dot added back, we will have the num, right? That's all. Let's try submitting the sample test cases. Now finally submit all the test cases. So we have successfully submitted our solution. Now the code of the problem is available in my GitHub repository. You can find the link in the description. Thank you everyone.